In the previous video, we've shown how you can take a differential equation, like for example the 1D Helmholtz equation, and then use a finite difference approximation to turn this into a linear algebra problem, into something of the form AX equal to B, with A being a matrix, these being vectors, and the only unknown is X, which you can then solve. But this video is a very general overview of different techniques that you can use to solve linear systems like this. The first thing that comes to mind is the direct brute force method, where you will use something like matrix inversion to solve this system here. So Gaussian elimination, basically. And then you might remember from your linear algebra courses, so if you use this, let's call this a direct approach, that this thing scales with n cubed, with n being the size of that matrix, the dimension of that matrix. So if you have twice as many grid points, then this thing becomes 8 times as difficult to solve. So that doesn't scale very, very favorably. However, this is the direct brute force approach, I would say. Another thing you can do, specifically for that example of the Helmholtz equation, is that you noticed that the matrix that we ended up with had a certain structure. So you had stuff on the central diagonal, and then stuff on these two adjacent diagonals, and then all the other entries were 0. So basically you have a tri-diagonal matrix for that specific example of the Helmholtz equation. Now that's good news, because obviously this is something that you can exploit for your solution of that matrix, and then you can have something more fancy than the general purpose algorithm, something that really exploits the fact that your matrix is tri-diagonal, and then the scaling factor goes down considerably. So now you have scaling with n squared. So that's good news. That's a much more advantageous way to solve this linear system. But can you do even better? Can you end up with something like order n or order n log n or something like that? Well, it turns out that there is a way to achieve that, and that's based on the so-called iterative methods. Now, what's the philosophy behind iterative methods? Well, that's the following. So, okay, we can solve this matrix as exactly as we can within the machine precision using techniques like this. But remember that even if we solve this equation exactly, the X that we will end up with is not the exact solution to the Helmholtz equation, because we've made a discretization error by going from a continuous domain to a discrete domain. And then we can say, okay, if our X is approximate anyhow, then perhaps we don't really need to solve that linear problem here to machine precision, and then we can live with an approximate solution to that linear equation over here. So that's the philosophy behind iterative methods, which start by some sort of an initial guess to your solution. And that initial guess could be, for example, the field 0 everywhere, or just some random initialization of the field, or perhaps you know the field of a slightly similar structure. So you just have some sort of initial guess. Don't worry too much about how wrong it is. But then you go to a magical refinement step. So you refine your guess, and then you end up with something that's hopefully a little bit more accurate than your initial guess. This is very abstract here, but later on I will say more about this. So you go from an initial guess to a second guess, and then you keep on refining and refining and refining until at some point in time you decide, okay, I have enough precision here. The difference between two successive approximations is good enough for me. Let's call it a day, and let's say the system has converged, and then I have my approximate solution, which is good enough for me. Now, this is very different from what we do here, and you might wonder, can this really be advantageous? Well, of course, that depends on a number of conditions here. First of all, you really do not want to need a lot of steps here. So you need a very clever method that quickly converges. And also very importantly is that you need to make sure that this refining step is something that can happen very fast. If you have these two conditions fulfilled, then you can have very clever methods that have very good scaling, that are very, very fast. And there's a whole zoo of different iterative techniques that could be the subject of an entire course. So we're not going to touch upon those. The only thing we're going to do is explain a very simple, almost embarrassingly simple iterative technique, the so-called Jacobi method, which unfortunately does not really work very well in practice, but it's good to illustrate how an iterative technique actually works. But that's for the next video.